In this video, I'd like to go through chapter 6 of your text, which is about metabolism in the cell. And it's an introduction to metabolism and talks about some topics that we'll be thinking about for the next month or so in this class. So let's go through the material, starting with 6.1. 6.1 is really an introduction to all of the ideas that you need for this unit. And it basically talks about the idea that a metabolism is what we call the system that's transforming matter and energy. So it's all of the chemical reactions that happen in a cell. And you may remember from early on in class, we looked at the entire graphic of all of the metabolic reactions that happen in an organism. And there are lots and lots of metabolic reactions. And it's the emergent property of life. So when all of these molecules are interacting, when all of these reactions are occurring, life is what comes out of that. So a metabolic pathway is just a term that describes a specific molecule that ends with another molecule, ends with a product. And along the way, you're catalyzed by enzymes. So if we start with A and we end up at D, the metabolic pathway says we'll go from A to B, and then from B to C, and then from C to D. Each one of these steps, A to B, is a reaction that's going to be catalyzed by an enzyme. So A to B requires enzyme 1, B to C requires enzyme 2, and C to D requires enzyme 3, and you put these all together to have a nice pathway from A to D. Now, if we have a pathway that's breaking down complex molecules, we're going to call it a catabolic pathway. So a common catabolic reaction is the breakdown of glucose into carbon dioxide and water. And along the way, we get some energy out of that, and we'll talk about that in a later chapter. On the other hand, an anabolic pathway consumes energy to build more complex molecules from simple ones. So making proteins from amino acids would be anabolic. You may have an easier time remembering anabolic if you think about anabolic steroids being used to help build muscle. So anabolic, building, catabolic, breaking down. This is all talking about energy. So whether we're building things up or breaking them down, we have to think about the energy that's in that system. And energy, basically defined, is the capacity to cause change. And there are lots of forms of it you may remember from physics, and some of those can do work. And we've already alluded in this class to how we use cellular energy to do different work back in the previous chapter when we talked about transporting things across the membrane. So just to quickly take you through all of the different types of energy that you could experience, you could be talking about in this class. Kinetic is energy associated with motion. Thermal is that kinetic energy associated with the atoms or molecules moving. So if you think about liquid water going to water vapor, those water molecules start vibrating more quickly. They're moving more randomly because they have more kinetic energy. Heat is going to be the transference of that thermal energy from one object to another. So that hot water vapor where the water molecules are vibrating really rapidly then comes in contact with a piece of metal, and those rapid kinetic energy, thermal energy, cause the molecules in the metal plate to move more quickly, making that plate to us hot as well, and that would be heat, the thermal energy transferring between the two. Light is another type of energy that can be harnessed to perform work, and just hang on to that until we get to photosynthesis. So we'll use light in photosynthesis to make sugar from carbon dioxide and water. Potential energy is energy that matter possesses because of its location or structure, and in physics you talked about this as, if you put something higher off the ground, it had more potential energy. We're going to, in this class, use chemical energy more frequently, which is going to be potential energy that's available because of the structure of a molecule. So it's potential energy available for release in a chemical reaction. And all of these types of energy can be converted from one form to another form. And we talked a little bit about this diving scenario where people who are on top of the diving board have more potential energy. As soon as they dive off the board, that potential energy becomes kinetic energy. So potential energy starts to drop, kinetic energy goes up. When they land in the water, they have much less potential energy than this person up here has. And if they want to get back up here, they have to put energy in they have to use the kinetic energy of muscle movement to climb back up the ladder, so that they now have more potential energy on top again. This is all talking about thermodynamics, and you probably remember that from chemistry, at least the phrase thermodynamics. That's going to be the study of energy transformation. So in an open system, it's transferred between the system and the surroundings. You probably, if you looked at this in chemistry, you talked mostly about closed systems, where whatever's in the system stays in the system. In biology, everything is open. So just keep that in mind, that everything we look at in biology is an open system. Things can come in, things can go out of our systems. The first law of thermodynamics is still in play, though. The first law is that energy can be transferred or transformed, but it cannot be created or destroyed. So no energy can be made or destroyed out of nothing. And that's the conservation of energy. So if we have energy in a system, it came from somewhere. If we get rid of energy in a system, it goes to somewhere. It doesn't just disappear into the ether. If you see this bear, I love the bear that we use to describe the laws of thermodynamics. The bear is getting energy from the fish. The fish got energy from the algae that it ate. The algae got energy from the sun. All energy comes from other energy. The second law of thermodynamics says during every energy transfer or transformation, some energy is lost as heat, or that every energy transfer or transformation increases the entropy of the universe. Entropy is disorder. So every reaction that occurs is going to create disorder or randomness in the universe. And the entropy of the universe is always increasing. So here's our bear again, and it's running. And as it's running, it's breaking down sugars to create energy for itself. It's creating more disorder because that one ordered sugar molecule is now becoming carbon dioxide, multiple carbon dioxide molecules, 6 of them, multiple water molecules, 6 of them, and all excess energy is being released as heat, which is thermal energy. So it's creating a lot more disorder compared to the single sugar molecule that bear was breaking down. So when we're doing this, we're creating organized things and we're creating heat. We would call this a spontaneous process. So a spontaneous process can occur without putting any energy in. And in biology, we're pretty much going to say that spontaneous things are going to be increasing the entropy of the universe. So if it's increasing the entropy of the universe, it will occur spontaneously in a biological system. So think about a cell. A cell is a much more ordered structure than the alternative, which would be just a bunch of molecules floating around. So all living things do is take disordered things and make them into ordered things. So cells take small molecules, make them into bigger molecules. They take components and build them into more structured things. And they do this to make an organism that can then take ordered forms of matter, such as food and things like that, and break them down into less ordered forms. So you have a cycle. Cells build things up. When they need to make new things, they break down big things to make small things. Those small things make energy, and they use those small things to build up new things. So energy is cycling throughout the system. And as we talked about with the bear and the fish, it's going to enter in the form of light and exit in the form of heat. So the light's going to enter to make the plants produce energy via photosynthesis, and at the very end of the day, it's going to be a decomposing pile of material that is warm because the heat is being lost to the environment. Often at this point, people say, well, wait. If we have complex organisms and we put a lot of molecules together to make something like a human, didn't we just violate the second law of thermodynamics? Didn't we just create order? And that's true. You can create order in a localized space, but every bit of order you're creating in a localized space, you have to be creating disorder somewhere else. So even though a small system might decrease in entropy, the total entropy of the entire universe is still going to increase. So you, as a ordered island of low entropy, go through your life creating lots of disorder. You create lots of heat, you create lots of messes, you eat lots of food, you break down lots of molecules. So it all balances out, and it has to balance out due to the second law of thermodynamics. And that brings us to 6.2. 6.2. 6.2 talks about whether or not a reaction is going to occur spontaneously, and we want to think about spontaneity as whether or not the free energy change of the reaction is positive or negative. So free energy is delta G, and free energy is energy that can do work when temperature and pressure are uniform in a living cell. And remember, in biology, we're going to constantly think about temperature and pressure being uniform and being constant. Those aren't variables we want to change when we talk about free energy. So free energy is the change during the reaction, and we'll think delta G is delta G final minus delta G initial. And so if you end up with more free energy than you began with, delta G final minus delta G initial is going to be positive. You increased in energy. If you end up with less energy than you started with, delta G final minus delta G initial is going to be a negative number, meaning you lost energy. Only processes with a negative delta G are spontaneous. And spontaneous processes can later be harnessed to perform work because that energy is being released from that process. You can think about free energy as a measure of a system's instability, and you want to get more stable. So another way to think about delta G is to sort of relate it to potential energy. So if you are on top of a table, you are more unstable. You have more free energy. You have more potential energy. The spontaneous reaction will be for you to jump off of the table or fall off of the table, because as you get to the ground, your potential energy is lower, your stability is higher, you can't fall off the ground, and if you take the potential energy from you on the ground and subtract the potential energy from you on the table, you have a negative potential energy, therefore it's a spontaneous reaction. You can see this in several ways, right? Diver, off the board, relation to gravity, high G, low G, spontaneous reaction. If we think about diffusion, putting all of the molecules in an ordered state in a solution actually requires a high amount of free energy because the entropy is rather low. It's very ordered. And then as we diffuse, we create more disorder. There is less free energy, a lower G. That's a spontaneous reaction from here to here. And same thing with a chemical reaction. We have a chemical reaction where we have a highly ordered molecule. As we go to disordered molecules, we lower the G. That also becomes spontaneous. All of these reactions have a delta G that's less than 0, and it's more stable at the end of the reaction. When we get to equilibrium, the forward and reverse reactions are going to be at the same rate. That's the same as chemistry. And that's the state of maximum stability. A process can only be working when it's moving towards equilibrium. Once it reaches equilibrium, the change in delta G, or the delta G, is going to be 0. And so you're neither going to be spontaneous or non-spontaneous. You're just going to be at equilibrium. Nothing's going to be happening. We can take this idea of free energy and apply it to chemistry of life. And we'll add some more words here, some more vocabulary here. An exergonic reaction is going to be a reaction where we have a net release of energy. Delta G is negative, and we can see this in a graph here. If we start with our reactants here, and we go to our products here, over the course of the reaction, we've released this much energy, the difference between the products and the reactants. So G final minus G initial gives the delta G, and this is going to be negative. This is an exergonic reaction. It's going to be spontaneous. An endergonic reaction is going to absorb free energy. Delta G will be positive. So here's our reactants, here's our products. Final minus initial is going to be a positive number. This reaction is going to require energy to be put in for it to work. This is endergonic and non-spontaneous. I like to talk about this in terms of these hydroelectric systems. So we can use them to think about how this works. So if we think about an isolated hydroelectric system, which is not the case in biology, right? Everything is open in biology, not closed. But here, the water is going to move from a higher energy state to a lower energy state. So delta G will be less than 0. And as long as this water is moving, the light will be on, right? Power will be generated. Once the water level becomes equivalent, right, we're at equilibrium, delta G is 0, you have no more energy in the system. The light does not come on anymore. Biologically, like we said, we talk about open systems. So in an open system, this delta G is negative again. Water is flowing through it, but now we open up a hole at the end, and we constantly pour more water in, and so this will stay as a negative delta G for the entire time, and will make energy as long as water's coming in and water's coming out. And by doing this, we can actually create a multi-step system, and this harkens back all the way to those metabolic pathways from the first slide. Now we put in some resource here, and as it moves through a series of steps, all of which are negative delta G's, we get a lot of different things happening and a lot of energy generated. That brings us to 6.3, where we're going to talk about how we couple this energy. So ATP is going to be the molecule that does a lot of our cellular work, and it's going to couple the exergonic reaction of ATP hydrolysis to all of the endergonic things that the cell might want to do. So there are three kinds of work in a cell: chemical work, transport work, and mechanical work. Chemical work would be, making and breaking chemical bonds. Transport is moving things across membranes. And mechanical is the type of work that you would see in kinesins or dyneins, motor proteins that are moving vesicles around inside of the cell. So we're going to couple our energy by putting an exergonic process next to an endergonic one, typically using ATP. And we've talked about ATP a lot in this class. It's a ribose, adenine, and 3-phosphate groups. And the energy is over here in the phosphodiester bonds. So when we take an ATP and we hydrolyze it using a water reaction we talked about in chapter 3, we will get an ADP, only 2 phosphates, an inorganic phosphate, which is just shorthand for that phosphate that came off, and energy that is released. Now, it's convenient in a drawing to just say this energy is released, but that energy isn't just floating around in space. It is actually being captured onto another bond, another molecule, and so that work can be done inside of the cell. So the energy from the exergonic reaction of ATP hydrolysis can drive endergonic, and we can do this typically by creating a phosphorylated intermediate. And I'm going to show you this in a series of steps here that we talked about in class. So glutamic acid plus ammonia to get glutamine. If we involve ATP, we're going to use the ATP to actually put a phosphate on the glutamine, and we're going to call that a phosphorylated intermediate molecule. And so instead of going from this to this, we'll instead go from this to this and then to this. All right, and why is this an important series of steps? Well, if we look at glutamic acid plus ammonia to give us glutamine, the delta G of this reaction is plus 3.4 kilocalories per mole. This is most definitely a endergonic reaction. It is not going to be spontaneous. Just because it's not spontaneous doesn't mean the cell can't make it happen. So what it can do is it can use ATP to phosphorylate the glutamic acid. This phosphorylated glutamic acid now has a higher free energy than the glutamic acid that has no phosphate on it. And the energy that it has came from the ATP. So now the ATP is at a lower energy state. ATP to ADP went down. Glutamic acid to phosphorylated glutamic acid went up. And now this reaction of the phosphorylated intermediate plus NH3 becomes spontaneous, giving us the glutamine. And when I say it becomes spontaneous, you might say, wait, how did it become spontaneous? It wasn't before. That's because of the coupling. So the delta G of the glutamic acid plus the NH3 to glutamine is a positive 3.4 kilocalories per mole. The delta G of ATP to ADP plus PI is a negative 7.3 kilocalories per mole. We just add those together, 3.4 minus 7.3 gives us a net delta G of negative 3.9. This coupled reaction becomes spontaneous, and it's going to happen. Lots of things are done by ATP hydrolysis. Putting that phosphate onto a protein is going to increase its energy, but it's also going to change its shape. And we talked about this when we talked about transport. So binding and releasing of a phosphate is going to open and close a carrier protein across the membrane to help you move things across their concentration gradient. Or we talked about how if we want to do transport protein, motor proteins like kinesin, we are going to bind an ATP, bind a phosphate. The phosphate is going to change the shape so that one leg moves forward, and then we're going to hydrolyze the ATP to cause the other leg to move forward, and this will cause this guy to walk along a vesicle. Walk a vesicle along a filament inside of the cell. ATP is going to be the thing that's used all the time by the cell, so it can be regenerated simply by putting that phosphate back onto the ADP. And we're going to use the energy of catabolic reactions to put the phosphate back on the ADP. And then we can use the ATP to ADP hydrolysis to do anabolic reactions inside of the cell. And look at this as a big cycle here. So energy comes in. This would be energy from food, for example, eating. You break that food down and use the breakdown to take ADP plus PI and turn it into ATP. Now the cells can use ATP and the hydrolysis of ATP to do cellular work, energy-consuming processes inside of the cell. So this is a cycle: exergonic, endergonic, exergonic, endergonic. Now that you understand how we can couple energy, we can talk about enzymes. We can talk about in 6.4 how enzymes are going to speed up metabolic reactions by lowering energy barriers. So a catalyst is going to be an agent that speeds up a reaction. You talked about those in chemistry. An enzyme is just a biological catalyst, and typically it's going to be a protein for us. So hydrolysis of sucrose by the enzyme sucrase is an example of this. And we talked about how sucrase, we know it's an enzyme because it ends with ASE. So anything that ends in ASE is going to be an enzyme, and the enzyme sucrase simply takes sucrose and helps us hydrolyze it into glucose and fructose. So the reaction that occurs when we try to break sucrose down requires energy to go in before we can break the bonds between them, and we call that activation energy, or EA. Activation energy is most often in the form of heat. So if you think in chemistry class, the way you would get most reactions to occur is you would heat them up. In biology, as we've talked about, it's not as easy to heat things up because living things have ranges in which they need to be to live, but we can use enzymes to sort of mitigate how much heat we need. So here is a reaction, the progress of the reaction plotted against the free energy. So if the reactants are here and the products are here, we can see that getting from reactant to product gives us a negative delta G. This reaction is spontaneous. The problem is, to get from here to here, you have to get over this transition state that has a higher free energy. That would be the energy of activation. So this much energy needs to go in to get us started, and then all of this energy will come out. It's overall spontaneous, but we do need to activate this reaction. Instead of doing heat, like I said, we're going to use an enzyme. So an enzyme is going to lower the activation energy. So now we have the same idea, reactants to products. It is still spontaneous. Enzymes do not affect the delta G. Enzymes only change the activation energy. So without the enzyme, we need to get to here. With the enzyme, we only need to get to here. It takes much less heat energy to start getting over this hump and to get over this hump, and consequently the reaction will occur more frequently. So the enzyme will speed up the rate of the reaction by lowering the activation energy. The enzymes are going to be very specific. So think about it, it's a protein. It has a very unique primary structure, secondary, tertiary, quaternary structure that's going to allow an enzyme to only work on one single reaction or a relatively small range of reactions. The reactant that the enzyme is going to act on is called the substrate. And when the enzyme starts to work, the enzyme is going to bind to the substrate, and we're going to call that the enzyme-substrate complex. So in the enzyme, the site where the substrate binds is going to be the active site. So here's the enzyme, here's the substrate. The substrate is going to enter into the active site of the enzyme. The specificity that I just talked about is going to work because the secondary, tertiary, quaternary folding of the enzyme is going to create a specific shape that fits the substrate, and that substrate is going to interact ionically, hydrophobic interactions, hydrogen bonding, all sorts of things to fit into the active site. And in some cases, the induced fit says that the enzyme itself is going to slightly fold differently so that the chemical groups of the active site and the substrate come in contact with each other, and that allows work to occur. Here's a great picture of it. So substrate fits into the active site, and you can see this enzyme substrate complex is actually sort of closed up around the substrate. The substrate binding the active site of the enzyme lowers the activation energy by doing things such as orienting the substrates correctly, straining the substrate bonds, providing a microenvironment for a reaction to occur, or covalently bonding to the substrate, giving it a higher energy so it can have a negative delta G later on. And here you see just in a cyclical form, substrates, they'll enter the active site. They're held in there by those weak interactions, ionic, hydrophobic, hydrogen bonding. Things will occur with the enzyme interacting with the substrate. The enzyme-substrate complex has a higher energy than the products, and so now we have a spontaneous reaction where we convert to products. Those products will be released, the enzyme is unchanged, and it can start over again. Every enzyme has an optimal temperature and pH, and if you think about the fact that enzymes are proteins and proteins are impacted by temperature and pH, you can see how the primary, secondary, tertiary, quaternary structure of the protein is going to maximize the temperature and pH that an enzyme can work at. You should be able to process a graph like this and say, all right, here's an enzyme that works optimally at 37 degrees Celsius, and as we get hotter, the activity of that reaction, the rate of that reaction goes down, and we eventually reach a point where that enzyme becomes denatured and no longer works. At colder temperatures, the enzyme may still work, but because molecules are moving more slowly, we get a slower rate, less reaction occurring. Other enzymes might be optimized for a higher temperature, so this enzyme is optimized for 75 degrees Celsius. It can operate at an entirely different range and can get to a much higher temperature before it denatures. Similarly, if we think about pH, enzymes in your stomach, for example, have to operate best at a pH of 2. So the structure of those proteins are going to be optimized for that pH. Things in your intestines have a higher pH, closer to 8, so they're going to be optimized for that pH. So if you think about optimizing an enzyme for pH and for temperature, for other things that will impact folding, you can get a lot of diversity in enzymes, and then you think about specificity on top of that. There are literally an infinite number of enzymes that could be created. Other things that help enzymes work are called cofactors. So cofactors are non-protein enzyme helpers. They can be inorganic, such as metal, or organic. When we think about metal, you might think about especially sticking one of those transition metals right in the middle of your enzyme, right in the active site. And transition metals will let you do a lot of electron chemistry inside of the active site, and we'll still say that's a cofactor, it's organic, because a protein wouldn't normally have a transition metal as part of it, but it can do that in this model of a cofactor. An organic cofactor is going to be called a coenzyme, and that's going to be things like vitamins that are required to help enzymes work. So you might have never thought about why you need vitamins and minerals in your diet, and vitamins and minerals are going to actually help many of your enzymes function by being cofactors for those reactions. Now finally, we talked about how enzymes are working. Enzymes can also be inhibited. There's two types of inhibition. You might have remembered this from the foam models we used in class. Competitive inhibition is going to compete for the same site, the same active site. So think about the substrate trying to bind the active site while the competitive inhibitor also tries to bind the active site. And it's really going to be a matchup of who has more numbers. So if there's more competitive inhibitor than substrate, the competitive inhibitors are going to block the reaction. If there's more substrate than competitive inhibitors, the substrate will win out and the reaction will continue to proceed, albeit at a slightly lower rate. Non-competitive inhibitors, on the other hand, are going to bind to another part of the enzyme, causing the enzyme to change shape and making the active site less effective at binding the substrate. And that was that example on the foam model where you stuck something into the side and you completely closed off the active site. If you use a non-competitive inhibitor, it does not matter how much substrate you add to the system. The non-competitive inhibitor isn't playing the game of trying to bind to the active site, and so it is going to continue to inhibit the reaction. Many inhibitors include toxins, poisons, pesticides, and antibiotics, if you want to think about the types of chemicals or molecules that would be inhibitors. Here's just a diagram of it. Normal binding substrate to active site. Competitive inhibitor blocks the substrate from going in. A non-competitive inhibitor changes the shape of the active site so that the substrate no longer fits. Now, as we think about enzymes, how enzymes function, how enzymes have temperature ranges, how enzymes have pH ranges, how enzymes utilize cofactors, how they have competitive and non-competitive inhibition, you can think about all of those things can be changed by single mutations in the genes that create the protein. So if you change a single amino acid, you're going to get a different folding. Potentially, you're going to get a different functionality. Once those things are altered, they might change the activity, they might change the specificity. And if that happens in an organism that the environment favors that change, you're going to create a novel form of the enzyme through natural selection. So, as we talked about for the entire year, tiny mutations that are beneficial to the organism are going to create new things in the population, and this is how we have such diversity in enzyme and enzyme function. And finally, we get to 6.5, which is going to talk about how we take all of the metabolic reactions and think again about that giant diagram I showed you of lots of reactions occurring, and how we regulate those to control the overall metabolism in a cell. So if everything was just doing the reaction whenever it felt like it or whenever the right things were in place, there would be chemical chaos. Everything would be happening all at once. And so you have to imagine that a cell is actually regulating all of the chemistry that's occurring inside of it, very carefully, very tightly regulating, by switching on and off the genes that create enzymes, or by switching on and off the enzymes themselves. So allosteric regulation is the idea that we can inhibit or stimulate the activity of an enzyme by binding somewhere else on an enzyme. This is very similar to non-competitive inhibition, except now we can either inhibit or activate by binding to another spot. And you can think about how when we bind in one place on a protein, we could change the folding anywhere else on the protein. And so by binding to the backside of the protein, we change the active site of the protein, things like that. So most allosterically regulated enzymes are polypeptides, like I said, and it has an inactive or an active form. So if we think about this being an enzyme, and it's inactive, active, inactive, active, inactive, active, it's going to be cycling between those states. And if we bind an activator to it, the active form is going to be the more stable form. If we bind an inhibitor to it, the inactive form is going to be more stable. And so as it flexes between them, we can add allosteric regulation to cause different things to occur. So here is a allosteric enzyme that has 4 subunits. As we cycle between inactive and active, it's either active or inactive, oscillating at equilibrium. Once we bind an activator protein to this, it becomes more stabilized in the active form, and now you're going to have more enzymatic activity happening in the cell. On the other hand, if you bind an inhibitor, it's going to be stabilized in the inactive form, and you're going to have less enzyme activity in the cell. And you can imagine by creating concentrations of activators and inhibitors at different levels, you can basically control how much enzymatic activity is happening at any one time. Cooperativity is another form of allosteric regulation that can help amplify activity. And in this case, we have an inactive enzyme that binds a substrate, And so even though it may bind this substrate at a relatively low affinity, once it binds the substrate, it's going to allosterically affect the other subunits, causing their active sites to become open and more active. So it's hard to get the first one on, but once you get the first one on, the next three will come on very quickly, and that's called cooperativity. The last idea, so we can take allosteric inhibition, we can take cooperativity, and we can look at this idea of feedback inhibition. And feedback inhibition is where the cell is going to be able to use the end product of a reaction to start off the beginning of the reaction. So all the way in the beginning of this talk, we talked about a metabolic reaction that goes from A to B to C to D. Feedback inhibition is going to say when we get finished making D, let's have D come back and inhibit the reaction from A to B so that we don't make more D. And so we can see here's an enzyme that takes threonine. Threonine binds the active site and it goes to intermediate A. Enzyme 2 makes it intermediate B. Enzyme 3 to C. 4 to D. 5 gives us the end product, which is isoleucine. So we've successfully taken threonine and turned it to isoleucine. Once the cell has tons of isoleucine, it no longer should be using energy to make threonine into isoleucine. And so the isoleucine actually binds to an allosteric site on enzyme 1. And when this is bound here at a non-competitive inhibitor, the active site is unavailable. And so you are no longer going to be making isoleucine in the cell. Once the isoleucine gets used up by the cell, for whatever cellular processes, it's going to leave the non-competitive inhibition site. It is no longer going to be inactivating the enzyme 1, and enzyme 1 will start doing its job again. And so these reactions can sort of cycle themselves by once they get to completion, they're going to stop working until the amount of product that's available drops again, and the reaction will start working again. And so these are all, complex ways that cells can regulate their total metabolism. And for now, I just need you to know the general ideas of how they interact. In the next few chapters, when we talk about photosynthesis and when we talk about cellular respiration, we'll see on a larger scale how these reactions can impact and affect all of the metabolic reactions that are happening in the cell.